Now you know multisim components usage. Using the multisim components with your theory will make your experiment simulations. What are the list of simulation experiments that we have done? These are the five, in which the experiment 3 can be of two parts: study of full control bridge rectifier with RRL load, and study of symmetrical full wave half control bridge rectifier with R and RL load. So let's see this rubrics. I will take example of a full bridge converter. So you have to draw the expected waveform. You have to draw the circuit diagram. Circuit diagram, which I did not write before, maybe. Circuit diagram, draw the expected waveform for the question. And then theory will have this part, theory, this section basically indicates explaining the basic working of that converter and any important formula. Like for rectifier, average voltage is an important formula. The RMS voltage may or may not be used. RMS voltage is also an important formula actually. The average and RMS value you will write. ACVC, the RMS value will be the important formula. So this much you will write. So where you can refer to get this theory, any book, any place. Here also theory is given in this document shared before. I will take example of single phase fully controlled bridge rectifier with R and RL load. Here the circuit diagram is given to you. This is the circuit diagram. Then you have your waveforms given here. Suppose you are asked in exam 45 degree. At 45 degree, you have to do the simulation. Then draw the expected waveform. What will be the expected waveform? This waveform only with alpha equal to 45. Everything remains same. This, if this is for R load, this remains everything same. For RL load, it depends what inductance you have given. You can draw this one itself if it is a continuous conduction. So two things happened now: circuit diagram, waveform, then explaining how it works in a brief manner. What is that? In a positive cycle, T1, T2 triggered. In negative cycle of the input AC, T3, T4 triggered. That much only you'll say. Then you will write and write the equation, average equation. What is the average equation? Average equation is simply that we have written before. Either you see that you can refer any documents, any online also. So example, full bridge, this is the circuit diagram. Either you draw that or this, it is same thing. These are the waveforms and the equation also is there. Equation will be available online. What is that? 2 Vm by pi cos alpha, 2 Vm by pi 1 plus cos alpha if it is R load. So these things you have to write in your first section. So this will give you a measure mark, which itself is a more than pass mark. So please focus here properly. This should be done by all of you. And exam rule is this section will, when you will be writing this part, first you have to write, then only you will go for simulation. And that time laptop will not be on. Everything will be off. You have to write the circuit diagram, waveform, and theory first. Then your laptop you can open and do the simulation. Mind it. After doing this part, you can move to the simulation part. After doing this, you can go to simulation part and you can open your laptops. Will ठीक है. Then simulation. Let's see the simulation part now. You understood how to write the circuit diagram, expected waveform, and the basic brief working of the circuit. of the converter. Simulation result, how to simulate, come to this point. I said we were discussing here last time. Any converter you make, you press the power section first, then the control section. What is the control section? This pulse voltage. For a full wave rectifier, full wave control rectifier, you need two pulses now. See, we need one pulse which is T1, T2. Another pulse is T3, T4. When are they given? This is alpha instant. This is how much? Pi plus alpha. And how much is this whole duration? This is 2 pi. And this again will be 2 pi plus alpha. One cycle repeats after that. So so we can say periodicity is 2 pi. This same signal comes, the pulse comes every 2 pi. And this pi plus alpha pulse for T3, T4 pulse, this also comes every 2 pi, but at pi plus alpha delays. Clear? Let me see if it is recording. Yes. Now you understood what we have to do, because this, if you know this is the theory part, then you know how you have to use the pulse voltage. You already know by the last video, just you have to put right values now. T1, T2, S1, S2 should have one pulse which is at alpha. And how you will determine what is alpha? Alpha is angle delay. Suppose I said 45 degree here. This alpha is 45 degree. Then last time we discussed the calculation also regarding this. So if the alpha is 45 degree, because 50 hertz is 20 millisecond, 20 millisecond in time domain, in radians will be 2 pi, and degree it will be 360 degree. So anything what you have to put here in the simulation is in time domain, so you have to convert this degree. When asked in terms of degree, you have to convert it in time domain. So if 45 degree asks, 45 divided by 360 into 20 will give you 20 divided by 8, that is 2.5 millisecond. That's why you put here in delay time 2.5 millisecond. This 5 volt, only 4 fields you are changing. This 2.5, then 20 millisecond, because it is 50 hertz sinusoidal signal. Pulse width is not required to change. Only this, and the delay. Delay is this, and this is the time period. Done. 3 fields. Now for T3, T4, what is the triggering instant? We said it is pi plus alpha. So pi plus alpha means if alpha is equal to 2.5 millisecond, and another signal which is coming at this point, T3 plus alpha, T3, T4, this pulse, this is coming at pi plus alpha. So pi plus alpha will be how much? If pi is in terms of time domain, 2 pi is equal to 20 millisecond. So obviously pi is equal to 10 milliseconds, and pi plus alpha is equal to nothing but 10 plus this term, which is 20 divided by 8, and this will come to be 12.8 milliseconds, 12.5 milliseconds. That's why another your pulse voltage need to be of 12.5 millisecond delay. Here what we have put 2.5 millisecond. But the periodicity of both of them is same, na? It is coming every 2 pi. This particular, we'll get back to this point. This signal is coming every 2 pi. And this will also come every 2 pi, one cycle. T3, T4 coming every one cycle. That's why That's why you will put the value as, instead of 2.5, it will be 12.5, because 10 plus 2.5. Remaining things will be same. Then it is for two thyristors S3, S4. Now, if you want to see the output voltage along with input voltage, last time I said if I want a input voltage is a differential, this point is not at the ground. So you can use the differential oscilloscope. If you want to see output and input together, if you are not seeing the output, then this is input, then is not required. You can use one oscilloscope with reference, common reference ground. This is the output. Now, if I simulate, see, always you can draw for R load, you keep the inductance, just make the inductance 0. When you have to see the waveform for RL load, you will simply change the inductor value to something positive. Then, see, again, this also we discussed, the waveform need to be taken within the window. So, window size need to be increased. Window size we are increasing. We have increased the window size. This waveform is for output is for full wave rectifier. You agree? Everything looks fine. Now suppose I make this, I close now. If I make 5 Henry here and again check the waveform. See, now it is a continuous conduction full wave rectifier. What else you need now? It is all done. Just two firing angles and the concept that S1, S2 triggered one time at alpha, S3, S4 triggered at pi plus alpha. That's all come from the theory, and remaining application of this, each of the components you have gone through in the previous lecture. So overall R and RL load you have seen. Suppose someone asks you about freewheeling with freewheeling diode, you will simply put one diode. Where do you get the ideal diode? Please, you can go to the power section. In power section, you have switches, diode. Okay. Whenever you want to rotate any device, you can press that switch, press that component, select that component and press Control R. Now it is rotated. What is the direction of full bridge? What is the direction of your freewheeling diode? This one. Now the waveform will be, we know with freewheeling diode, the output waveform looks like a R load output voltage waveform. So with R load, this was the waveform, and with RL plus freewheeling also we have this kind of waveform. This is all done. Now suppose you are asked few other things. You see, what is the conduction angle of, now suppose you want to see the current anywhere here for any thyristor. So what is the current in this thyristor? Because it is not within the window, let's make it within the window. See, current for the thyristor is still the full, same as the time when your voltage output is positive. So if someone asks you what is the conduction angle, what is the conduction angle, what you will do? Normal and triggering it at single. Then you will simply move the cursor. This time basically is from alpha to pi, which is approximately equal to T2 minus T1 is 8 milliseconds, something like 8 milliseconds. So, not exactly 8 milliseconds, it is 7.6 milliseconds. So 7.6 millisecond or 7.5 millisecond is your conduction angle. Conduction angle, this also come from theory. What is conduction angle? In a time for which SCR is conducting. If it was not a freewheeling diode, then your conduction angle will be higher. Now the thyristor is conducting for a longer time. How much time is the thyristor conducting? From here to the full pi, that is equal to 10 millisecond instead of 7.6 millisecond. Got it? This particular, this is your thyristor current. What polarity of the current we have taken, our direction of current we have taken opposite. That's why we're getting negative current. Done with this. Now you know everything about this converter and potential things that you need to observe here. Another thing that we are observing, what we are doing, we were observing what is the output average voltage. You know by equation for suppose RL load, if your output waveform is like this, what will be the average voltage equation? 2 Vm by pi cos alpha. So by that equation, putting cos alpha of alpha 45 degree, cos 45 degree and Vm based on 230 into root 2, you will get what is the average voltage from this equation, from this waveform. But if for this waveform theoretically, now if you see, just to match if your simulation is correct or not, you can take this volt. This also we have discussed last time about this particular meters. Here I have put this meter. I am putting the current meter also here. Okay, so this is taking the series, the through current, and this is the taking the node voltage. What is node voltage? Instantaneous value is given here. We have said we want DC voltage. 146 volt is the DC voltage, that is average voltage. Now from the theory, 2 Vm by pi cos alpha cos 45 is equal to your average voltage, and that should be equal to 146 degree. Done. That much only. You don't need to make a table and do it for different alpha. You will be asked for one alpha only. You will be asked for one alpha. It will not be for multiple things, only one or two questions related to how similar to how we have discussed now. This page we are all clear with here with this one now. Now successful simulation done. Some questions also we have seen to get the average voltage from the simulation, and then calculating the average voltage from your uh, theoretical equation, that is 2 Vm by pi cos alpha. Then some other observations like you can you have seen that with RL load, your output voltage was continuously reflecting, and you had negative voltage component in the output voltage with RL load, and SCR was conducting for longer, conduction angle was 10 millisecond with RL load, and with R load it was 7.5 millisecond. So these basic things can be there in the questions on your simulation results. Done. So this experiment is successful. So any other experiment, if you see half bridge rectifier, what you will do initially, you will make R the circuit, then you will put the pulse voltage, and it will give you similar wave. Everything implementation is similar to the previous full bridge rectifier that we see. The R load means inductance will be zero. Then for RL load, you will make this another value, another positive value, which will be specified to you. Then with freewheeling diode, simply you will put the freewheeling diode later. So three parts, no need to do it multiple time. Only one time circuit will be made. Then you can edit, delete each of them, and rest of the things are same. Then AC voltage regulator is also similar circuit, just that you had a reverse connected SCR. So you will get your output voltage in a negative cycle as well. So it is basically another AC voltage where its RMS is a variable. So it is a fixed input RMS of 230 to a variable output RMS voltage converter. So here RMS voltage equation you have to write in the theory, and the circuit diagram waveform and the expected waveform and the basic working principle. And you need to show this waveform and draw the circuit as you understood. That's it. Then you compare. Questions can be similar to that. What is the conduction angle of this thyristor, this thyristor? What is the current? What is the voltage value? What is the voltage value at some instant? What is the conduction angle? What is the average voltage? Here is zero, obviously. What is the RMS voltage? How the average voltage can change if I switch the some basic questions will only be asked. Understood now. No, RMS value you can get by the equation you have theoretically. Then you can compare. Here you can see 163 volt is the RMS value. You can compare both of them. Now the three-phase half-bridge converter. Similarly, everything is similar. Just you are using this converter because it gives you better flexibility in when alpha is. See, this circuit, if I play, let me stop this one first. My output voltage will look like this. Because this I said is at 0 degree and alpha starts at 30 degree only for a three-phase converter. What we did here, basically every individual phase voltage is taken and compared with the alpha input, which is 46 now, that is 46 degree. If it is at 30 degree, alpha is equal to 0, because we know for a three-phase half-bridge rectifier, alpha starts from angle 30 degree. So at 30 degree, around 30 degree, if you are specified some particular value, you can double click this key voltage. Maximum value I said I should keep 180 degree. When I'm changing it, and keep 1% increment, that will make it more flexible to move it. Now suppose it is 30 degree, around 30 degree. It is giving you a simply alpha 0. At angle 30, we know alpha starts, alpha is 0 here. Though alpha is by the key voltage, we know it is set at 30 degree in reference to the main sinusoidal supply, but the actual for three phase alpha starts at 30 degree. That's why you are seeing a diode rectifier kind of waveform. If I increase it further, like 15 degree alpha, then how much it will be? 30 plus 15, that is 45 degree. So if I set it at 45 degree, it will give this kind of waveform. If I set it at 90 degree, it will give this kind of waveform. Then you can see the same thing. You can put the meter here. It is giving you average voltage of 145 volt, and you can calculate the average voltage by your theoretical equation. It should be similar. You can change the inductance value, then waveform will have a different behavior. Like that only, every converter that we have seen, those are basically rectifier and AC voltage regulator we did for the four experiments from experiment 2 to 5. So they will have similar implementation. All clear? This has two individual phase voltages with respect to the ground, and then the alpha. Alpha says the angle itself with respect to the 0 degree. So 93 degree time is for alpha equal to 93.6 minus 30. Now, the first experiment was this one. I will save and close this part. First experiment, You simply you can write the theory like what's given in your manual. What is written in the rubric part. Suppose you will draw the characteristic. For SCR, you will draw this characteristic. So for the MOSFET, you will draw MOSFET characteristics that you have drawn in your practical copies. Then you will write what are these different region, reverse breakdown, forward conduction, latching, holding current. What are those terms that you will write in the theory? Draw the expected for experiment one, draw the expected characteristic, circuit configuration. What is the circuit configuration to get the uh, waveform? What are the things you are wearing? You are wearing the voltage at the switch terminal, anode cathode, and you are checking the current through the anode. So you can show what are the things that you have to measure in the circuit itself. So this kind of circuit you can make for both MOSFET and your SCR, MOSFET IGBT SCR. MOSFET, you can see, you will for Hyster we are discussing now. So you are say you are varying this basically. So you can show this variation in the variable voltage in the circuit. Then you are varying what exactly more than this. You are varying the voltage. You are checking the current. That's the first part. And you are also varying the gate voltage and checking multiple such curves. So you are varying this also. So you can simply show the circuit in this manner, and it will be done. And then some important latching current, holding current definition. Suppose saturation for MOSFET, you can write what is saturation region at your linear region, cutoff region. That much will come in the theory. That's it. Now simulation is this is simulation. You can see you will be specified which thyristor you have to use. Here we have used 297 29700. You can always go to component when everything the part number is specified. You can directly go to all groups and suppose I can search in the question it is given. Do it for 2977700 part number MOSFET. So you will simply click that one and press OK. Similarly for the thyristor. So for MOSFET we are keeping this series resistance very low because we want that our MOSFET saturation curve should also be captured. This resistance does not mean much for the MOSFET because we know gate current is very low. Then what we did here to simulate the curves, basic circuit is this much only. You have to just go to analysis simulation. This thing was at default interactive simulation, which was fine for all the simulation from experiment 2 to 5, but for one, it is DC sweep. Then you take V2, you can name them as well. I will name it, suppose VGS. This is VGS. So display level VGS. Okay. Then I am writing this one as VDS because where it is connected. This is drain, this is source. So at drain source you have connected this voltage. Now what I have to do, these meters were not required. If you only want to check the instantaneous values, then you can put these meters. It is here in the multimeter section. Otherwise you can remove it when you want to simply get you simply vary these parameters. You are setting it to 5 and 100 volt, but when you will vary this na analysis and simulation DC sweep, it will not be required because it will simply vary them by itself. VGS I am varying at every 5 increment till 60 volt. This particular MOSFET has a breakdown at 60 volt. So and gate voltages for which I am going to plot this is suppose 0, 5, 10 and 15. So I will have 4 steps here and with the increment of 5. So what it will plot? it will plot, we want to plot ID versus VDS, suppose. So ID is the output. ID is money current going into the MOSFET ID. So ID is nothing but IR1, IR2, this is IR2. But since current default direction is this in this manner, that's why I am writing here IR2. I will show you exactly what expression we have taken. With respect to this, we are getting the current. Current is IR2 that we want to see, but direction is reverse. So I will write add expression IR2, double click. Before IR2, I will write minus negative. Now it is expression is minus of IR2. Okay, minus IR2 selected. I will save this. Source that we want to vary in the x-axis is VDS. Therefore, it will be in the source one. This is VDS. So your curve will be ID versus VDS. ID versus VDS at different gate voltage VGS. So we are doing it for sentence will be like this. We want to plot the output current with respect to the x-axis voltage at different VGS voltages. You'll save it now. Now if you run it, you'll get the MOSFET characteristic. The name can be changed later. Similarly for SCR, you simply right click it, replace component. Suppose in SCR you have used, I have already prepared that before, so I will open. So SCR we are using this one. Here current limit is higher, so we are putting 100 ohm here. If I if you'll check the analysis and simulation, what we want to plot in SCR, we simply want to plot current versus the voltage V2. Therefore V2, IV2 is what you want to plot, and at different V1. V1 is here, but I want to the gate voltage node voltage here. This is V4, this point. Therefore I write V4 here. Then I save. Then I plot. We will not get SI characteristic by this one. We have to actually take the Excel sheet, which you won't need to do in the exam. You will only need to the MOSFET characteristics are obtained directly. You don't need any Excel sheet part. SCR we needed it because it does not plot in the same sense, because we want the gate current to plot basically at different gate current we want to plot, and we don't have any DC sweep option in same manner. That's why SCR you will be asked to draw the circuit and then you write the theory in both of for both of the MOSFET IGBT and SCR characteristic theory, basic theory as a region of the your characteristics, and your draw the characteristics, draw the circuit diagram, and then simulate it. Your waveform will be obtained for SCR in this manner only. The actual waveform will not be obtained. For the MOSFET, we have already seen that we get good waveform similar to like this. Now all of the experiments are revised to you and hope it will be uh, easy for you to do now. Theory part, already you have studied this for class test and all. Theory parts are limited for this five experiment that you have to only see these five type of circuits and their theory. And theory is scoring mark, so you should understand, write it properly. For the semi-converter part, symmetrical half control bridge rectifier, what you will do? It will simply become, you will remove, suppose it is a symmetrical configuration. I will simply delete, suppose this one, and I will replace this SCR with a diode, control R, and this SCR symmetrical configuration. This is a asymmetrical configuration. So, okay, I did one thing wrong here. No, nothing wrong with this guy. Fine. This should also be replaced by diode. Okay, control R, select control R. Now you see this is nothing but a full bridge half control rectifier with two diodes in a symmetrical configuration. This circuit is. Now if you see the output waveform, even with inductance, you will see the freewheeling effect. Output voltage does not have negative current. That is what theory says na? About a single phase full bridge half control rectifier. And what is the conduction angle? Cool thing is conduction angle is for the SCR. We are seeing S1 na? S1 current is conducting for 10 milliseconds. You see here to here. This is around 10 milliseconds. That is half cycle. But SCR output voltage comes only for pi minus alpha, that is conduction angle, which is 7.5 milliseconds. Done. All the experiments done. Thank you.